So just let me quickly review what I discussed in the last session. So first I discussed about the cooperative game and its allocation rule, mainly safely value and core solution. Then communication situation, network games and its some solution. So what is a communication situation? That the first Myerson in 1977 introduced a graph theoretic idea to analyze about the cooperation structure in cooperative game. If we have a cooperative game, as I said, in the cooperative games, player have some strategy to cooperate with another player and then from coalitions, right? And V is a function, if N is the set of agents or players, V is a function on, the domain is the set of all coalition, it's a real value function with the restriction that the empty coalition will always generate zero value. So then what is the communication situation? So for each cooperative game, right? So we can have a n into n minus two numbers of graph. And G we are saying that G is the class of all graphs on n, where small n is the cardinality of players, the numbers of players in that set. So then for each graph system, for any Z, the people we call a communication situation. Each cooperative game we associate with another, with any of graphs we call a communication situation, where we can define an associate cooperative game. How we define the associate cooperative game? If I say V restricted to Z is a one associate cooperative game, so and it will be over all. So it will be sum over all the partition of S. S restricted to Z is a one kind of partition of the coalition S over Z. So this is how we define a communication situation and the associate cooperative game. And this associate cooperative game is nothing but it's again a cooperative game. So here we can define all the allocation rules for cooperative game. So one of the cooperative allocation rule, we can talk about the safely value. So you remember how we define the safely value? We define the safely value is actually for any particular player. I for the game N and V, its overall coalition S. So non-empty coalition. Oh, we consider empty coalition here. If S is a subset of any coalition of n minus I, then some coefficients here, and it is considering all the marginal contribution of I. So this is how define a safely value. So the safely value that defined for this game, the safely value that defined for this game is actually we call the Myerson value for the communication situation, and we associate with a graph G. So then we say there are some drawbacks for the communication situation. What are the drawbacks for the communication situation? The drawbacks is that, say for N is the 4-player game, there are 4 agents, then the graph structure does not matter. So we can have this kind of graph structure, right? So for any player set, they all are connected via any part, either it's complete graph or there is a less, say.
As long as the component is same, it doesn't matter how they are.
Yeah. So somehow they are connected via some part, but it doesn't matter how they are connected. So under any communication sheet, any graph or this graph or this graph or this graph, the communication situation will give the same value. So then after that, so there is a one game was introduced to generalize this idea and say the value of the graph should depend on the what. The structure of the graph actually should depend on the what of the yes. So that game we call a network game. So in the network game we have a pair N and V, where V is the domain for the V is what? Set of all possible graphs on N. So where the graph structure depends on the value generated by the value that will depends on the graph structure. Okay, the graph structure matters how they can generate the what. It depends on the graph structure. Okay, then we talked about the Myerson value. Okay, then we talked about some allocation rule. So once we have a network game, once we define the network, so then we can talk about allocation rule, how we are going to allocate them in a fair way. So there are two types of allocation rule. So first is player based. So in a player based allocation rule, what is do? First we allocate the players in the networks. So one allocation rule we talked about the Myerson value, right? And second we talked link based. Then we consider each link as a hypothetical player, and we define a link game, and then we allocate the link first, and what are the allocation for the each link, then we really distribute among the players. So then we talked about the position value, right? These both are based on Chevalier value. Okay, so then we have a characterization based on the class of VCA, component entity value function, and the value function, just a class of all value function that are not component additive. Do you remember what is a component additive value function?
Worth of the graph is sum of worth of all the private components.
Yeah, components, right? So, okay, if I have a more component, then the total words if Z has some components, say Z1, Z2 like that, then whatever the word of Z, it will be sum over all its component like that. Okay, so then, so let me first erase this whole part. Okay, then we have another also allocation, egalitarian allocation, link based, component wise, and then bunch of link based bunch of value. Then other two will have. So if I will have some more time, then I will discuss it later. So now I want to talk about some criticism of Myerson value. So now we are discussing about the fixed networks. Those are fixed network where we have one network Z, right? So we call it a fixed network. So now when we define the Myerson value, then we have some criticisms. So what is the criticism? So it's clear, the picture is clear to you. So here, this is a one, same graph. It's a network with player 1, 2, 3, where 1 and 2 are connected, and 2 and 3, it's a pointer. Okay, so 1 and 2 is connected, 1 and 3 is connected, and 1, 2 is connected, 2, 3 is connected, 2, 3 is connected, and 1, 3, and 1, 2, 3 is isolated, 2 is here isolated, and 1 is isolated. Okay, and this is a complete network. And the game phi is how is defined. So it's only one for this network where 2 has a 2 connection with 1 and 2. If 2 doesn't have any connection with any one, then the what is 0. Even though 2 has a connection with 2 and 3, the what is almost 0. 2 is connected with 1. Again 1 and 3 is also connected, the what is 0. And when 1 and 2 is connected, the what is 1. 2 and 3 is only connected, then what is again 1. So this is how it is defined, the game is defined. And you can see here the player 2 is generating more. In presence of the player 2, when he is present in that network, so he is generating more. So definitely, so one can say that, so he should get more payoff, right? So then we have another game. So this is first game V we defined. There is another game, say V prime is defined, that everywhere, it doesn't matter the network structure, so every network is generating 1. Right? So here the thing is that, so is everyone is equally distributing, generating the same word, so they should get equal payoff, right? So but if you calculate, then you can see, does not matter for B and B prime, for the network structure 1, 2 and 2, 3, it will give the Myerson value, give the same payoff, right? So in V, as I mentioned, the 2 is generating more, so definitely 2 should get more. But in the V prime, under V prime, every network, it doesn't matter the network structure, so everyone contributing same at the network, whichever the network structure, so all words what are equal to 1, so they should get equal payoff, right? So but under the Myerson value, still this player 2 is getting more than other players, right? So somehow the network structure sometimes doesn't matter. So in this case, we can say. So then, so another concept it was introduced is called flexible network. So for that flexible network, first we define a monotonic cover. So what is a monotonic cover? So it consider, so V bar or V cap, it actually takes the maximum watt of any subgraph. Okay. So Z is a one network. For example, say it's a complete network 1, 2, 3, 2, 3 and 1, 3. This is a complete network on the 3 player, and say it is generating 2. The complete network is generating 2, but say 1, 2 and 2, 3 is generating more than the complete network. So then the monotonic cover for Z will be what? 4. Right? So it will consider the highest value subset of over all subgraph of Z. That's how the monotonic cover is defined. Any question? Okay. So then a flexible player-based allocation rule was defined. How it's defined is simply
You just take maximum.
only it will take the maximum monotonic cover. So it's based on the monotonic cover. It is same as the Myerson value, but only it's considered a monotonic cover. And it's a ratio of what is the actual watt of VZ and what is the monotonic cover of the whole complete network. Right? And for this particular player-based flexible network, we have a different kind of, yeah. Yes, yeah, subgraph, all subgraph, yeah. We will consider any maximum value we have to go. Is actually we can consider equal also, it itself also. Here? This example? No. This example, right? I was talking about this example. Yeah. So here this example, as I said, the watt for this network is 4, but for watt for this network is
2. So it will consider, and other words are like 1, say 1, 3, 2, 3, right? So yeah, 2, 3. The word for this is 1 and say 1, 2 and 1, 3. This is again what is 1, right? So it will consider only the maximum highest value which is generated by any subgraph of that J, right? This is how the monotonic cover is defined, and this is how it's defined. Any question? So for this kind of allocation rule, we have a different set of axioms. So one first is equal treatment of vital players, weak additivity, and so these are okay. These are two axioms that was axiomatized. Okay. G to the power n. Yes, yes. No.
In the big cap, G to the power S million. This is the summation. Within sigma, you have a, yeah.
This one? B to the power cap, yes.
Yeah, is it the complete network with S million?
Yes, yes, it's a complete network. It's considering the complete network, right. Complete network considering with the players S union I. Right. Yeah. So that's actually, I was using this notation. Earlier I was using this notation. So this both notation is almost same. It's actually what? Induced subgraph, right? Yeah, it was the induced subgraph and that other one is the complete subgraph. Yeah. So no, these two are different. These two are different. Yeah. The induced subgraph and complete subgraph is different. Yeah. Or yes, the complete graph we have to consider, and then it will be any maximum value of what? So Z start G of S union I P of G prime. It will consider any maximum value, right? Any question? Okay. So next, here I have a one simple example. It is a more generalized example, but say I have V and V prime, where you can see that in the V, the 2 is generating more, right? So under this flexible network player base, definitely 2 is getting more than the another other than 1 and 3, and so in the V prime, everyone is generating 1. No, everyone is generating omega. So some constant game. It's a constant game, and everyone is getting same payoff. Right? So if you use the earlier formula, and so this expression, just use this example, then you will have this payoffs. Okay. So what I wanted to mention that, so in the Myerson value, sometimes the player's rules doesn't matter. If player is generating more or less, sometimes it will get a payoff. So it may, I mean, some player, so in case here, I can say that 2 is generating more, definitely. So one possible in a fair way, we can say that 2 should get more. But say for another example, free 5, so both all players are equally generating. So, but somehow another Myerson value, still 2 is getting more, right? So in these cases, so that flexible network was introduced with the monotonic cover was introduced, and then we have this flexible player network games, and then the one player based flexible network allocation was introduced, and then we can see then, so then for the first, definitely players are getting according to their contribution, and in second case also we have the same kind of fairness allocation rule, right? So this is what I want to talk about, flexible network. So then, is it okay? Is okay? Okay, this I want to talk about this part, that network formation part. So we have discussed lot of networks and some allocation rule. Now the main question is that how such network structure form and what should be the characterization for that. And so what are the incentive for individual, for each agent to form a link with another individual, and that leads to a bigger structure of a network, and that should satisfy some measure of efficiency. Right? So this is the main question. So for that, so what is the measure of efficiency? So there are three types of efficiency was introduced: efficiency, Pareto efficiency, and constraint efficiency. This constraint efficiency, Pareto efficiency, and efficiency. So you can see this efficiency is similar to a monotonic cover, not exactly similar, it's almost similar to monotonic cover. So what is the efficiency actually? If a network Z which called is efficient with relative to V is a game, right? Then the word should be more than any another network G prime for all Z. Z is actually what the class of all networks on N, right?
All the nodes are utilized, so it becomes efficient.
I mean, I can say that for any sub networks, say Z, I can say it will be efficient. Say this is my Z, right? I can say this Z will be efficient, right? If the worth of Z is more than any other network that belongs to Z. So it could be a this kind of network also. Okay, let me use different. If we add more link, but it will not generating more than J. Say if I remove this link also, then it will not generating more, right? So only Z we call efficient if it is the highest generating, if it can generate the highest value, right? For any graph that belongs to Z, Z prime belongs to Z. Clear? So next is Pareto efficiency. So what is a Pareto efficiency? So Pareto efficiency also associated with the allocation. So efficiency is only associated with the value that the game, but Pareto efficiency also associated with the allocation rule. So under suppose Z is a one network and there is a one allocation rule Y on G, right? So then what is the allocation rule? So what is the allocation rule for Y on Z should be greater than any other allocation, under the same allocation rule for any Z prime. So this Z is efficient with relative to V and Y when there should not be exist any allocation rule for any G prime which should be greater than this allocation. That's why it say that there is no allocation rule and there is no G prime any other subgraph or on G such that this will happen. So Z is Pareto efficiency with respect to Y and V if we will not have another graph G prime such that under that allocation rule the G prime for the G prime will get more payoff. Okay. So here, this efficiency, if network is efficiency only if the definition is associated only for V, but in case of Pareto efficiency, it should be associated with V and allocation rule both. Okay. So next, we have a constant efficiency. The constant efficiency is what? Is the same as a Pareto efficiency, but only there are two things that Y should be component balance and anonymous. Do you remember what is a component balance? So we define it on the class of component additivity. So what is a component balance?
This component has
So suppose Z has a two component, the component balance will be what? The total watt that generated by the component G1 should be equal the total watt that is generated by the component G1 should be equal to the allocation rule that belongs to the players in that component. So whatever players in this component, they should be equal to the whatever that graph will generate, right? So similarly for Z2 also, the players who are belongs to the component G2, their allocation rule should be equal to the value that was generated by this graph G2, right? So this is the definition for component balance, and the next I have another definition of anonymous. So what is anonymous? So if I have a one graph Z, right?
permutation.
Yeah, permutation, the simply is that we level the players in a different way, then definitely, so for this permutation the graph structure will be changed. I mean the graph structure will be same, but only the leveling is different. So under this graph, if we define a under permutation game like that, B of Z, and the allocation rule for the player I in this GV, it should be equal what are the permutation player in that I in this game G prime and V prime, right? So it is actually same like that symmetric. Also we can say if two player contribution is same in two different in the same game, so they should get the same payoff. So somehow it is also same, but this anonymous is the more generalized concept than symmetric concept. Okay. So second, the third definition is the constant efficiency is almost same as Pareto efficiency, only that we have to consider that Y is component balance and plus anonymous. So these are the three definitions of efficiency. First efficiency, Pareto efficiency and constraint efficiency. So then any question you have? So this concept are very so this concept are not that difficult concept, right? So very easy to understand. So now there are some relationship between all this efficiency, definition of efficiency. What are these? EB, the class of networks that are efficient on B, the class of the networks that are constraint efficient should be contained, and this is actually the class of all. P is actually what? The class of all Pareto efficiency. This class is bigger than CE than E. So each classes contain each other, right? Okay. So I am just here mentioning only the exam results only. So I am not going to do any proof because it will take a lot of time to prove all of this, right? Okay. So any question regarding the efficiency, right? So this is how the first question, this is how we define the measure of efficiency. So next question, we try to say, okay, this is how defined. So now we'll talk about some network formation, right? So for that, so first model was about pairwise stability. Okay. So first The paper, as I mentioned, Jackson and Walensky 1996, this concept was introduced, pairwise stability. So this is also very easy concept, and it's a very weak condition concept also, weak notation also, because it's only consider a one link. Suppose I and J is connected in G, and for whatever I is getting under Y, if I delete the link, then he will get less. Okay. Suppose Z is here, I and G is connected in G. If I delete the link, I and G, right? Okay, let me erase this part. So this is something, it's like that. This is my G, the structure of this G. G is connected like this way, where there is a one link between I and G. So whatever I will get under Y, right? Both I and J get under Y should be greater than after deleting this link, right? If I delete this link, then I and J should get less, right? This is the first condition. The second condition is that somehow there is no link, okay? Okay. Somehow there is a no link between I and J, and after, if they want to form a link, but I is getting more, but J is not getting more after forming that link. So one is benefited, but other way, the another one is not benefited. Okay. So it will say one is getting more here, I is getting more, but J, when the link is not there, J was more benefited, right? This is the second condition. So a network we can say pairwise stable when there is a, if we delete the one link, if two player, for any two pair of player, if we delete the link, then they will lose, and if there is no link, but somehow they want to form that link, but one should benefit and another should not benefit it, right? So this is the pairwise stability concept. So then only we can say that the network is stable. So pairwise stable. So we here check the pairwise stable, and this is associated with a one link at a time, right? Any more question? Any question you have? So this is a very simple concept. So now here is a one situation we can say. So this pairwise stable network. So here the network is not stable. So let's see. So suppose I have a two player. So 1, 2, 3, 4. So let's talk about this network. 1 is isolated, 2 is isolated, somehow 3 and 4, they formed a link, and after that they got some equal amount. Let's say it is 7, 7, okay. So say somehow they are got equal amount. So here we are not talking about some particular allocation while like Myerson value, position value, anything. It's any allocation rule we are talking about, say, right. So then, say 1 and 2 here, those are isolated, right. So definitely they also try to form another link, because after forming that link they will get more benefited, right. So definitely from here and this network will form, right. So remember the first condition, that if I delete the link, then they will get more benefited, right. So here the first, according to the first, 1 and 2 is not connected here, but when they are formed a link, here they are getting 0 payoff, right, but now they are getting 7, 7, okay. So after that, if between 1 and this is 4, this is 1, 2, 4 and 3, 4. If say 1 and 4 form the link, right? Already 1 and 2 link is there, 3 and 4 link is there. If 1 and 4 link is formed, right, in this network, their allocation rule is 7, 7. Now they are getting 8, 8, and the agent 2 is getting 3, agent 3 is getting 13. Right? Earlier their allocation was 7, 7. So definitely they try, all of the players try to form this link 1 and 4 because they are getting better payoff than this network. Right? If I say this is network Z1, this is Z2, this is Z3. Right? So now see, somehow if we delete this link, then what happened? 1 will get more and 2 will get less, right? So definitely 1 will not try to form another link with 2. The second condition. Yeah. So no. So after that, from here you can see that 2, 4, the player 4 is getting 6 in this network Z4, but here he is getting more. So no network is stable under this allocation rule. So this was one example on trad network. So that was described, it was mentioned in a survey paper by Jackson, Matt Jackson. So you can have a look at this, how this allocation rule was distributed. So for the particular scenario, okay. So here is a one example. We can see that the pairwise stability is sometimes not exist, does not exist, okay. Yeah. You are talking definition. So first definition, yep. So first definition, if we delete a one link, then the player will get less payoff, right, after removing the link. And if we want to add a one link, one player will get more, but another player will get less. Yeah. So let me erase all of this. This is Z1. Which one? This one? From Z4 to Z1? Are you talking about Z4? Z3. G3 to Z4. Okay. As I said, so from here to this, but the second condition, right? Second condition, right? Say from 1 and 2, if they try to form a one link, one player will benefit it, another player will not benefit it, right? So one is getting less, but 3 is getting more, so that the link will not form, right? This is what? So this is actually Z3 is actually what? Z4 plus 1 and 2 link. So under this 1 he is getting 8, but earlier he was getting 11. If I talked about Z4, I think, okay, correct. So here he is getting 11, but here he is getting 8. So, but another player is 0 to 13. So definitely he is getting more. But he doesn't want to form this link. One does not want to form this link. Why? Because he is getting less. So he is not get any more. So that he doesn't have any incentive to form this link. Correct? That's the second condition. So second condition was right, right? Right. One is getting more, another is getting less. Right? So here is a one example. The network is stable. So if we talked about the pairwise stability here, right? So it's a one circle. Okay. So then, so in the example we said that that not exist in some settings, but so here we have a 3 results. So what are the results that? So the under Meyerson value, there always exists a efficient allocation rule, efficient network which is always pairwise stable. That's the first result. The second result, egalitarian rule, and third one, component wise egalitarian rule. That is the equal division. See, egalitarian, do you remember what is egalitarian? That if the what? It is equally distributed among the players, right? And what are the what of that component? That is also equally distributed among the players in that component, right? That is component wise. And we can say this is what the allocation rule, egalitarian allocation rule is balanced, but this is component wise is component balance. Okay. So these are the class of allocation rule where we can say there always exists a one efficient network that is pairwise stable, right. So next, here I have another axioms. Here we talked about constraint efficient, that there is no allocation rule, there does not exist any allocation rule which is anonymous, and component balance where V is efficient, at least V have a one efficient network that is pairwise stable. So we do not have this kind of constant efficiency, okay, that is pairwise stable. So we do not have. So we can't have this kind of efficiency which is pairwise stable, okay. Any question you have? Right. So next, before that, several. Okay. So I want to talk about some criticism about pairwise stability. As we can see, the pairwise stability we can it satisfies only a very narrow class of allocation rule. Those are, we can say, Meyerson value, egalitarian value, and component egalitarian value, right. So it's a very small class of allocation rule. We can say if there is a one efficient and network is pairwise stable. That's a one drawback. Second drawback is that is only consider a one single link at a time, right. So suppose a player who has a more link, and if he delete by adding his, say one player, he has a more link, and by adding a set of links or removing some set of links, he will get more benefited. So that from, so pairwise stability we can't say that, okay. And second thing is that suppose a group of individual, say, so pairwise stability always consider a pair of players and the link between them. Suppose if we have to talk about a group of player, so at the same time they can say will get more benefited after rearranging some the network structure, right. There some link, but somehow that pairwise stability does not consider all of this, okay. So that's why the pairwise stability concept is very a weak concept, weak notion, and for that there is some another concept was introduced, okay. So it's almost 10 o'clock, let's have a break, okay. Then after the break we will discuss another some concept. So here there are some drawbacks for the pairwise stability, but here I have another definition. It's called critical link monotonicity, that's also related with pairwise stability. So first of all, a link Ij, suppose in a network Ij is connected, right. in the network G. So after deleting the link, if G has a more component, then we can say this link is critical, right. So now this is G is whole connected. If I delete this link, then G will have a two different component. This will be one component, this will be another component, right. So this is G1 and this is G2 and whole network is G. So then I can say that I and G, this link are critical, right. So now let us see what is a critical link monotonicity, right. Okay. So for example, you say that A is denote a component that contain a critical link. Say this is the whole H component that contain this critical link I and J, right. And after deleting this link I and J, I will have two more component H1 and H2. H is the whole component that contain the link I and J. So after deleting this link I and J, I will have two more components, that H1 and H2, right. So the pair G and V is another game that define on G, right. Critical link, okay. Just a minute, it should be H I get. It is not G, it should be H, okay. So then H and B that satisfies critical link monotonicity if whatever the word for the word that generated by the whole link, a whole component H should be less than when they are generating individually sum of their whatever the worth of H1 and then H2. If we sum all of them, this should be greater than when the H is generating that worth, right. And this is the one allocation, and this allocation will be what? So this particular player, say I and J is there in that network H, right. So how much he is getting is, this is actually what? This allocation rule we call component wise Euclidean, right. So I simply say C and E, component wise Euclidean, right. So in that component H, the allocation rule is what? V of H divided by total number of player in that component H should be less than equal to what is the maximum of what is the maximum of the allocation rule for a player in H1 and H2. These are two what? H1 and H2 components allocation rule. It should be what is the maximum among them should be less than when the player in that component. Then we call this kind of notion is called critical link monotonicity, that associate with a one link, critical link, right. So it is clear, the definition is quite simple. If there is a one critical link in a component H, after deleting that link we have a two different component H1 and H2. So whatever a particular player I will get in the component H, that is the component wise pairwise component wise Euclidean rule, that is V of H divided by number of player in H should be less than equal to the maximum of whatever the player will get in that H1 component and H2, right. So there is a one theorem then So G is efficient where V is component additive, and if G will pairwise stable for this component wise egalitarian rule if and only if this pair satisfies this critical link property, monotonicity. Right? So we have an efficient network that satisfies the pairwise stability for this allocation rule, component wise egalitarian allocation rule, if and only if that the pair this Z and V that should satisfy the critical link monotonicity. If I will have a one critical link, then it should satisfy this critical link monotonicity. Okay, this is a one characterization also we can have for efficient network, which is also pairwise stable. And this is only for component wise egalitarian rule, not for another allocation rule. Right. So earlier we have this 3 allocation rule. For under this 3 allocation rule, if we have it, there always exists a one efficient that is pairwise stable, right, for Myerson value egalitarian and component wise. But here here we have only for component wise egalitarian rule. We can't say similar kind of theorem for in case of another axioms like Myerson or component balance or Myerson and egalitarian rule. Okay, we can say only this particular allocation rule, right? Okay. So next, as I mentioned, so there are lot of drawbacks for pairwise stability because it's considered only a single link at a time. Okay. So it's a very weak class, narrow class of, it satisfies only very narrow class of allocation rule. So now there is some alternative approach of network formation that is called strongly stable. Okay. So there is another paper, Jackson and Nolan in 2004, they introduced this idea of strongly stable. So it also implies this pairwise stability also, but so how it actually, this is the interpretation part. So before that, let's have a look at the definition, how it was introduced. So for that, the first definition we need is called, what is the network Z prime is obtainable for Z via deviation by S. Suppose I have a one network Z prime and there is another network Z, right, and this network Z prime is obtainable from Z via deviated by S. S is any coalition of N, right. So let us see what are the criteria for that. If there is a one link in Ij, suppose that link Ij is not here, that is a part of Z prime. Somehow Z prime and G, maybe there should be, their intersection should be non-empty. It may be empty or may not be empty, that we do not know. Okay. There are some, probably there are some link in their intersection, right, and say Ij, that link is belongs to Z prime, not in Z, then we can say that this the agent I and J should be belongs to S, right. In another way, the second definition, say I and J if I and J, this link is a part of Z, not in the part of Z prime, then this I and J should not be belongs to S.
Does that somehow mean we can't delete edges
that's mean that so it's just that the G prime is obtainable, say from Z. So by deviating that C, right, it's like that only, yeah. So suppose I have a one set of players that's already part of G prime, they are not part of Z, right. So this mean actually what, S is a part of G prime, not the part of G, and G prime is obtainable from Z means, yeah, if we want to delete some link or add some link from G prime to Z, yeah. So second definition is a network is strongly stable with respect to Y and V only when that in G prime, so in say in G prime, so in G prime there is a one particular player who is benefited in G prime, but the other player is not benefited. So somehow its meaning is that is some particular player, so they want to rearrange, if they are benefited after rearranging their network structure, right. So that this is so that's the they are talking about that's involvement. So there are a group of players, after rearranging that they will get more benefited, then they would definitely want to do that. Suppose the set of players, say talks about this player set A's, right, in a network G prime, they are getting more, they are more benefited. So then definitely they don't want to rearrange their network to some other networks. So it's mostly involve a particular set of group. It's an involvement of set of group which are only benefited in the network G prime, not in the, they are not benefited in G. So definitely they don't want to rearrange their network structure from G prime to G. This is what we can say about the interpretation. So mostly that this is the technical part, I mean, but interpretation is like that. So there are a set of groups, they are generating more or they are getting more under the pay of Y, but in the another network say Z, they are not benefited. Say particular player is not benefited, so then they don't want to deviate to another group. They don't want to rearrange their network structure. It's like that, right? Okay. So this strongly stable concept is associated with a set of player. Suppose it is associated with a one particular player to a pair of player, then we can say it is also similar to pairwise stability concept. Okay. The question you have? So this definition is little bit technical, but the interpretation, as I mentioned, that is associated it is the involvement of one set of group. Suppose in a network they are more, their payoff is more, but in another network one particular player is if one particular player is getting more but another player is not getting more, then they don't want to deviate to, they don't want to rearrange their network structure. So this is the whole concept of strongly stable network, right? Okay. So let's move to this theorem. So this is a one theorem where somehow this is actually defined that Y is not connected, Z is not connected. This is a one partition of N. So this partition of N is what? Say suppose Z is not connected, like it has some component like this. And pi of Z is what actually? It's a partition S1 and S2, where S1 is what? The players who belong this component S1, and S2 the player who belongs to this component, right? So it's definitely a partition, right? So I am saying that when pi of Z is equal to players at N, that means it is connected, complete. You say one single component, right? If it is not equal to N, that means it is not totally connected, it has some component, right? So then first consider that Y is anonymous, component decomposable and component balanced. These are some axioms that we consider, but I want to just mention you that a network is strongly stable with respect to Y and G, where then we can say the allocation for Y will be component to Y's Euclidean allocation rule. So if a allocation rule, so suppose V is component additive anonymous, that is given, then we can have a allocation rule that is anonymous, component decomposable and component balanced. So I have not discussed about component decomposable, but I discussed about other. So suppose there is a one allocation rule that is strongly stable and that is also anonymous component balanced, then we can say that this could be a allocation rule which is actually a component wise Euclidean rule, right? So but the converse we can't say, this is only a necessary condition, the sufficient condition is may not be true, right? So if we have a strongly stable network, that is also Y V is component additive and anonymous, and Y is if we have an anonymous and component decomposable and component balanced rule, then we can say this allocation rule is nothing but that component wise Euclidean allocation rule. Okay. So now let me just tell you what is a component decomposable. So say component decomposable is actually what? Say for example, say this is Z, this is a Z1 and this is Z2, right? So Z has a two component, right? So whatever allocation in G is almost similar to the component balance, but the only thing is that, see suppose what is the number Y is getting, say a particular player, I will get under the allocation rule for the bigger network Z, right? And if we remove this part, if we remove all the component and suppose if we consider only the component Z1, right? So then the allocation rule for the Y will be same. So what I wanted to say, suppose a particular player is belong to a one component, right? Whatever his allocation rule, if we consider only that component, and say if we consider the whole bigger network also, then it will be same. So it's almost similar to component balance, right? Okay. Do you have any question? So statement is what? That if there was a one strongly stable network Z, and on that network if we have a one allocation rule that is anonymous and component balance, and if we have a allocation rule that is component balance, component additive and anonymous, then that allocation rule will be component wise Euclidean. Okay, this is the statement, right? Okay, so next we have another statement. So this statement is, we have a sufficient and necessary condition. So that is also similar to, that is also associated to a core solution. So what is this actually? So we have a network Z with respect to V, that network will be strongly stable, right? So suppose we have a network Z, this network will be strongly stable associate with a Z and V, and whatever allocation rule we are going to define on this network structure, where V is actually what? Anonymous and component additive value function, and the allocation rule Y is actually what? Components wise egalitarian. So, if and only if this condition will hold when we define another associate cooperative game. So, suppose this is my NV, right, and Z is the network structure, that is my network game. So, on this network game, if I define a cooperative game, how I am going to define the cooperative game? That cooperative game will be WV as, for any coalition, it will consider the maximum of Z, GS, it is what? The complete network of the players S and B of J. And if we can say the core of this cooperative game is non-empty. In the first class, I think first lecture I mentioned about core solution, right. So, if a network game is, cooperative game is convex, then we can have a non-empty core, right. So, what is a convex? Remember what is a convex game? So, suppose S1 and S2, these are two coalitions, right. So, this is my S1 and S2, like they might be disjoint or not. Then whatever their total watt should be greater than their individual watt minus their one intersection, right. So, I only mentioned about this theorem that if for a convex game core is non-empty. So, there is another if and only if condition also there, that is based on the balancedness that I did not discuss. So, it is mentioned that, so we have a strongly stable network, we have a strongly stable network with respect to V, where V is component additive and value function anonymous, and the allocation rule, component wise egalitarian allocation rule, if and only if we define a cooperative game VW, where we consider that the watt is equal to the maximum of the watt of any network that belongs to the complete network G over S, right, GS. So, if the core will be non-empty, then if and only if this condition satisfy, this efficiency or condition will satisfy this then we can have a strongly stable network which is also efficient, right. So, proofs are very lengthy, that is why I do not want to discuss here. So, if anyone interested, just let me know, I can give you the papers. So, I can provide you the papers, okay. So, or what I can do, or I can give you the old papers to Kartik, then he can upload anything, right, okay, if you want. Okay. So, I just want to mention about this. I do not want to discuss because these are non-cooperative approach, and besides pairwise stability and strongly stable, there are another two models. So, first it was in 1988, Omen and Meyerson, they discussed about this non-cooperative approach. So, in a non-cooperative game, player have some strategy, and after that we can have some kind of equilibrium. So, one famous equilibrium, say Nash equilibrium, right. So, similarly, so they used this approach. First they define a non-cooperative game, the player will say which form they are interested to form, So after that, so they define a one equilibrium for that. So this is a one non-cooperative approach. So then there is another non-cooperative approach. It's Bhaskar Datta and Suresh Muthuswamy, date 1997. So they discuss about another game, and they talked about like this solution concept, Nash equilibrium, strong equilibrium, collision proof Nash equilibrium. They talked about this kind of Nash equilibrium. Okay. So now Bhaskar Datta is currently in Ashoka University. So earlier he was in a UK. So now the another person as Muthuswamy, he is a faculty in economics in a institute UK. Okay, so apart from my habit, okay. So there are some questions, right? Open questions are there. I want to mention you what are the open questions. So first question is the dynamic approach. Still this paper, Watts 2001 and Jackson 2000, Watts 1998, they had an approach of dynamic approach, but a complete dynamic approach is still missing. So when the network will form, it's a dynamic process, right? Suppose the one link will be formed, then another player will definitely will be affected after forming that link, right? So similarly, so another network link will form, so rest of the player will definitely get affected with after forming that link. So this should be a dynamic process. So this kind of dynamic approach is still missing. So this is a one open question. So how we can talk about that dynamic process of forming a series of a sequence of links.
How do you see game theoretic approach and static?
Which one?
Second.
Static.
The above definition is both static and dynamic.
Yeah, static, right? Because we are talking about the fairway stability is like we are talking about one single link at a time. That is the static process. So this is what I am mentioning. So saying strongly stable condition is also a one particular set of player, right? And we are talking about whether this player will prefer the network G or G prime, right? So it's a static process. So for the dynamic process, as I mentioned, suppose there is a one link, it will going to form. So whatever the rest of players, how they are going to react for that. Suppose there is another player, say K and L, the link will form. Then how the player will get affected after forming this link? So it should be a one by one process, right? So it's so network formation we can consider it's the formation of sequence of forming of some link, right? It can be a sequence. So it should be happen over time. So it's a dynamic approach. So over time, the network structure will change. How all the player in the network will get affected, like that we can discuss. So suppose first step, this network is happen, then the second link is happen. So again, we can talk about just another player M and L. They form the network like that, form the link like that. Over time, the network structure will change, right? So how we can model this full dynamic process? So no one has talked about this approach. So this is a one question, right? So similarly, there are another two open questions are there. So the first question is that, so no one for special, I mean, people have modeled some link formation that is strongly stable, pairway stable, another two model I mentioned about non-cooperative approach. But whatever particular problem, so this model will fit in this situation, but another model will fit in this situation. So no one talked about that. So for particular reason, so we have a different kind of model, but we don't know which model will be the best fit for this kind of situation. That no one has discussed. Second, these all models are theoretical model. So in real life, we don't know how this network will form, So there is no empirical study about it. So no one discuss any empirical work on network formation. So these are all theoretical. In real life, if we have some data, can we think about a empirical work on networks formation? Right? So these are 3 questions I want to mention you. Okay. Again, so we have mostly talked about, say for strongly stable, we say we have only talked about the allocation rule that is strongly stable if the network is efficient, also strongly stable, and only allocation which consider that is component wise Euclidean allocation rule, right. So similarly for pairwise stability also we have a Meyerson value. Under this Meyerson value we can say that efficient allocation rule is pairwise stable under Euclidean and under component wise Euclidean rule. But I mentioned lot of allocation rule, right, in the last class also. So we can have this much of allocation rule, or we can talk about more allocation rule. If for different situations, some allocation rule will, if we apply some allocation rule, so player will get more benefited, right. So no one is talked about efficiency and pairwise stability or stability condition for the other allocation rule, right, for the Meyerson value and mostly component wise Euclidean allocation rule. But what about the other allocation rule? So no one has talked about it, discussed anything about it. There is no modeling of other allocation rule. Okay. And also I want to mention in the last class, last lecture, I was talking about Meyerson value, position value, right. So when I mentioned that there are some characterization for Meyerson value on the class of component additive and on the class of V, that is not the component additive value function. So one characterization for I mentioned for Meyerson value was what? Component balance under the, right. So it will be, say, component balance and equal bargaining power, right. And another I mentioned that component balance and balance contribution, removing one player. So it is a equal bargaining what? Removing one player link, right. So similarly it will be balance and equal bargaining power and balance and balance contribution, right. So similarly position value we can have a 2-3 kind of axiomatization. As I mentioned that axiomatization is what? There are a particular set of property that will satisfy only by this property. Okay, if a allocation rule Y just satisfy one set of axioms, then we can say this is the only allocation rule which satisfy only these axioms. There is no other allocation rule which satisfies this particular set of axioms, right. So like Meyerson value, these are the 2 allocation rule like that, right. So people only talked about the characterization for Meyerson value and position value. So there are some other allocation rule, though it was introduced in network settings like Euclidean, link based Euclidean, component wise Euclidean, the core solution, right. For this there is no characterization theorem for this. Okay. So one can talk about their characterization. What could be the characterization for that? For any cooperative game, we say that always sometimes core may be empty. So what under another what condition we can say for the network games the core will be non-empty?
I think there was a theorem which said that if V is anonymous and component.
No, that is different. I am talking about that is different. So I know you were talking about we define a associate allocation rule. Are you talking about this part, right?
I think the axiom implies that.
Yeah. I remember. Yeah, you are talking about this. This is different. This is different. See, this is a cooperative game. Previous one here.
This implies by C is.
No. I am saying this is in case of strongly stable when I have a efficient network and under what condition the network will be stable like that. So that what I am saying here, it is different. So suppose I have a one allocation rule, and how I am going to characterize, that is here the efficiency and stability condition that I am not considering. Okay. Okay. So again, there are some characterization for network bunch-up and link-based bunch-up value. So this is multi-thread iterative value is different value. I just want to show you this property. What is a pairwise merging property? Is simply if I have a network Z and suppose I merge two players with all its link. Say 2 and 3 I want to merge. 2 were one player. Then I will have this merging network. How it will form? After merging 2 and 3 player to a 1 player P, the network 2 and 4, the link 2 4, the link T4 will become a 1 link 4P. So this link will become only this link, 1 link, and we do not have this link. So this is how we are merging two player, and after merging the player we will have a different network structure. If this is my original network and here the player 2 and 3 are merged into a new player, that is called P, right. And then if NV is a one network game, we define a network game V. So but here my player set will be what? 1 P, P is what? The player 2 and 3 merged here, 4, 5, 6. So earlier my player set will be 1, 2, 3, 4, 5, 6, right. So here I merged the two players, so my network structure is different. So now I can define a one different game. Here V is the original game, but here I am defining another game. That is a network game, right. So that is also based on original game. Okay. In the next slide I will show you. So this pairwise merging property is saying what? So whatever the allocation rule for the player 2 and 3, the sum of the players allocation rule. So I have the network games, right. This is my network game. I can define any allocation rule, say minus and position or anything, right, equal division or component wise equal division. So any allocation rule, say Y and 3, whatever the allocation rule in this network, the sum should be equal to the allocation rule for the particular player 2P in this merged network and the reduced game that we define on V bar. So this is we call a pairwise merging property. So with the help of this property we can axiomatize the bunch-up value. Okay. So next here I want to show you, these are very technical. These are the actually how we define the pairwise merging property, and this is how we define that reduced game on V bar. I can say this is V, it is mentioned as Vij, which is equivalent to V bar. Right. So these are a little bit technical, but whatever I want to say that, so similar kind of, this is also a similar kind of pairwise stability, or I can say that we just merge a 1-2 player into a 1 player and we have a reduced network game, and from that network game we can have this kind of allocation. So sometimes what happens, so if my network is, so it will be benefited when, so if my network structure is very huge, so what we can do, we can pairwise merge the whole player, then we have a small kind of network, right. So and we can calculate the game itself, then it will easy for us to calculate the allocation rule. Or if you want to do some coding, then it will also help, because in coding we have a less networks. because we have in the Mars network, we have a less network, and it will help us to do some calculation or help us to do coding, right? So that's why this property is important. So I was discussing about this paper. You can have a look at this paper. So I was mostly using this paper, the Zakshan-Ulinski 1996 paper, and there is a one book also. So this mission, so he was talked about this position value for communication situation, and it was his master thesis. Okay, I mentioned you earlier, right? It was his master thesis, and he talked about position value, right? And anything? Yeah, first Myers in 1977. This was the paper when he talked about first introduced the idea of communication situation. And this is the Shapley value I was mentioning. So this was the paper when he's introduced the idea of the Shapley value. Yeah, okay. So mostly I was following these papers. Okay. Okay. Yeah.